I'm going to talk about Oblivious LWE sampling using quantum algorithms. And this talk is based on joint work with Thomas Devry and Damien Estelle. So let me start with the definition of one-way functions. A function f is one-way if it's easy to compute, but it's hard to invert, meaning that no polynomial time algorithm can invert f of un as a random variable. So one-way functions are fundamental primitives in cryptography. As a use case, you can think of the input as the secret key and the output as the public key. And the one-wayness guarantees that no polynomial time adversary can find the secret key given the public key. And this raises the question of how we can sample from f of un. The naive sampler samples in a string R uniformly from the domain and then evaluates the function. So this sampler has a particular property, and this property is that whoever is doing the sampling algorithm knows the secret. In this talk, we're interested in samplers that can sample this key pair or the f of un, but without knowing the inverse. And we call such samplers oblivious samplers. A possible candidate of an oblivious sampler is that we can sample is that we sample some string y uniformly from the range. But the problem is that not all one-way functions fall in this category. One can also think of a possible oblivious sampler that is quantum. So here we call it the superposition sampler, an example. So in this superposition sampler, we construct a superposition of all outcomes of the function. And if we measure this quantum state, it collapses to one single outcome of the function f. The issue with this kind of sampler is that generally they require inverse of the function. So as I said, in this talk, we're interested in the oblivious samplers, but not for arbitrary choice of one-way functions. What we are going to use is the LWE one-way function. So let me explain what it is. Let A be a matrix, m times n, with integer elements. So the associated one-way functions to this matrix S sends two vectors S and E to AS plus E mod Q for some choice of integer Q. So S is an n-dimensional integer vector, E is an m-dimensional integer vector, and E is chosen such that E is chosen to guarantee that this function is injective and sparse. So the domain of E is limited. So the one-wayness of the function, which is also known as the LWE assumption, says that when A is sampled uniformly, S is sampled uniformly from ZQ to the N, and E is sampled from the Gaussian distribution for some appropriate standard deviation sigma, which represents its density function by chi sigma to the m, which m represents the dimension. In this setting, it's hard to invert AS plus E mod Q. So what I just explained is a naive sampler for the LWE one-way function. So an interesting question is so first of all, so this naive sampler is clearly not oblivious. An interesting question is whether we can build an oblivious sampler for LWE. And the answer is we don't know. And this problem seems so difficult that some people try to build cryptography using this no answer. So basically, the assumption that is used in this setting is the LWE knowledge assumption, and it says that there's no polynomial time oblivious sampler for LWE, and it's used to analyze the security of several cryptographic protocols. In this talk, we break this assumption in a quantum setting, and as a consequence, our construction of oblivious sampler invalidates the security of mentioned protocols in the presence of quantum adversaries. So as the general idea, we're going to use the superposition sampler. So we are going to construct a superposition of all LWE outputs, which we also call LWE instances. The superposition of LWE instances, which we also call LWE state, is something that looks like to this state, a superposition of AS plus E, which the amplitudes that correspond to S are uniform, and the amplitudes that correspond to the noise E are chosen to be distributed as the square root of the Gaussian distribution. If you measure this state, you will obtain a well-distributed LWE instance. So let's start with let's start. So as I mentioned, this building the superposition generally requires the inverse of the function. So let's start to see how it looks like for LWE. So we can build the superposition of the secret S in one register and a superposition of the noise E in another register efficiently in polynomial time. Then we can add the multiplication of the A of the matrix with the first register, with the secret, to the second register. And this can be also implemented in polynomial time. And imagine if we have a LWE inverter, an LWE solver, then we can apply that solver to the second register and subtract the result from the first register. So in this way, by kind of uncomputing the computation, we unentangle the first register and then we throw it out. And you can see that the result is the LWE state. But of course, this is not polynomial time because we don't have polynomial time LWE solver. So recently there was a different approach by different authors. So let me explain what they do. But for the sake of simplicity, first let's assume that A is just a single row. We do the same as before, but be careful that the noise state is one-dimensional now. So they observed that the second register, it contains a little bit of information about the secret S in the form of an inner product with the row of the matrix A. And if you believe me, if you do the math, for the arbitrary choice of A, this gives many of these quantum states that encode information about the secret S, but with different linear combinations. So they called this, they tried to define different notation to interpret this register differently. And for example, let's cite J to be defined to be the superposition of J plus E with the amplitude being the square root of the Gaussian distribution of E. Then the second part of the register, like the m-dimensional rightmost registers, can be decomposed into m simpler registers, each of which indexed by A transpose S, where AI is the ith row of the matrix A. So each of them contains some information about the secret. Now, if we can extract the secret S from these M registers in a way that we don't destroy them, and then we subtract the result from the first register, we are done. And I'm going to explain how we can extract this information, or how CLZ extracted this information. But before that, we observed that this is this is an instance of the so-called unambiguous state discrimination, in which we are given a bunch of states, let's say psi1 to psi q, which they have a particular shape. They are translations of each other for some amplitude that is known. And then we are asked as a distinguisher to determine a state that is given to us. So in other words, there's a challenger that chooses one of these states arbitrarily and sends it to the distinguisher, and distinguisher is supposed to find what this state is, but under some condition. It's not allowed to make any mistakes, but it is allowed to say that I don't know. So we represent this don't know answer with some special symbol but. And the success probability of the distinguisher is the probability that it can detect correctly the answer. So the CLZ, they did not use this formalism of unambiguous state discrimination, but if you dig into their techniques, you can see that they basically demonstrated a distinguisher for this problem, and the success probability of their distinguisher is proportional to minimum of Fourier coefficients. Now, having this distinguisher, one can apply it to these M register independently and obtain either like a don't know answer or a linear equation. And if we have sufficiently many linear equations, we can apply Gaussian elimination to find the secret. So I cheated a little bit here because by applying this distinguisher, we are possibly applying quantum measurement, and it possibly destroys the quantum state. But we didn't want to destroy it, because if we destroy it, we don't end up in the LWE state. I'm not going into the details, but the idea is that we don't actually apply the distinguisher, but we purify the distinguisher and the Gaussian elimination. It allows us to extract S without changing the state. For the details, you can see the STOC24 paper or our paper. So as I said, if we have sufficiently many linear equations, we can find a secret S. And if you've noticed, so we need a requirement here to have sufficiently many linear equations, and the requirement is that M must be larger than N over the success probability. And N is the dimension of the secret S. And if you, again, do the math for our particular choice of size states, we end up with this lower bound on the quantity of M. So if I want to summarize what CLZ did, they built the LWE states, the LWE state under the condition that M is larger than N squared times e to the pi sigma squared. So this has two issues. So first, the lower bound is exponential in the standard deviation, and for typical choice of a standard deviation, which is usually to be equal to N or a polynomial of N, this is exponential. And moreover, in some applications like a SNARK, Q is also chosen to be exponential. So this lower bound is the product of two exponential quantities, and this is not good. And also, so they didn't specify the runtime or the circuit size of the distinguisher or their sampler. I mean, the algorithm that they built for that they used to build LWE state. But if you do the naive implementation, it's polynomial in M and Q, which is also exponential. So can we improve this? We actually observed that the CLZ distinguisher is not optimal. There's an old work in '98 that they demonstrated an optimal distinguisher for the task of unambiguous discrimination, and the success probability of their distinguishers is like Q squared times better than the CLZ distinguisher. So it helps us to decrease the lower bound with Q square, decrease multiplicatively the lower bound by Q square. And they also didn't specify the runtime of their distinguisher, but we could implement it in runtime that is polynomial in logarithm of Q. But we are not done yet, because the lower bound on the quantity of M is still exponentially a standard deviation. And this is kind of a barrier because, as I mentioned, this is optimal distinguisher. We cannot expect to improve it. So what can we do? We actually adopted like a different strategy. We observed that it suffices to build a quantum state that is not exactly equal to the LWE state, but it's equal to LWE state up to some local phases. So if you measure this LWE state with phases, you'll end up in the same distribution of the outcome, because the phases, they do not affect the outcome distribution. But the question is, do they really help to improve the success probability of the distinguisher? So let me give an example. Like, assume that Q is equal to 2. So we have two quantum states, psi 1 and psi 2, and assume that the alpha and beta, they are not 0. And actually, we observed that phases, they do help to increase the success probability of the distinguisher in for these two quantum states. And we can choose the simple imaginary phase here for the amplitude beta. And then if you compute the inner product of these psi tilde states, it equals to 0. And this means they're perfectly distinguishable. Unfortunately, this technique cannot be generalized for the arbitrary choice of Q. We cannot make them to be perfectly distinguishable. But we also observed that the sign function actually suffices for our purpose. The sign of E is defined to be +1 if E is in 0 to Q over 2, is between 0 and Q over 2, and -1 if E is between minus Q over 2, 2 minus 1. And the sign of a vector is defined to be the product of the sign of its components. So we could show that this sign function is surprisingly strong enough to allow us to build the quantum LWE state with signs. So let me explain how. We do pretty much the same as before, but we also add this sign phase to the noise state, and this can be implemented efficiently using a controlled gate. And now we end up in a new psi state, which we call psi tilde, and if we can extract S from these new states, we are done. So how does this extraction work? So we apply the CB distinguisher, and then we apply the Gaussian elimination. Of course, it's in the purified way. And so, as we know, the explicit formula to compute the success probability of CB distinguisher as a function of the amplitudes, and we know the explicit quantities of the amplitude, they're Gaussian with signs. Then if you do the math, you can see that the success probability would increase to 1 over sigma, where sigma was the standard deviation of the Gaussian distribution. So this gives us a much smaller lower bound for the quantity of M. So if I want to wrap up, we generally show that as long as the amplitude function is an even function, then adding signs increase the success probability of CB distinguisher to to be f of 0 squared. And using that, we can build the LWE state with phases. So I just want to add that this approach is extendable to cover exponentially large standard deviation. And for the details, you can read the paper. And you can find the full version of the paper at these two links. Thank you for watching this video.